So what we're going to do is have a look at refraction through a perspex block. So here we have a perspex block. Place that in line with our laser beam, and we can see when the laser beam is going into the block at 90 degrees to the surface, or what we call along the normal, the light pretty much just goes straight through. You don't really notice any difference. However, what's happening here is refraction. Refraction is the change in speed of light when moving from one medium to another. The light here is in air, traveling at approximately 3 times 10 to the 8, that's 300 million meters per second. But in the perspex block, it's slowing down. It's actually traveling more like 2 times 10 to the 8 meters per second. And then as it exits the block, it speeds back up again, going at 300 million meters per second. If I draw a dot just where the light exits the block, and another dot here along the line, and then remove the block, I can connect all of those together to show the path of the ray. Now that's not really very useful because we don't have a reference point. So when we're drawing these diagrams in physics, what we tend to do is to draw a diagram of the block. So here I have a blank sheet of paper. I'm going to place my block. I'm going to mark a point on the block here where the light is going to enter, and that's going to be where my normal line is drawn at 90 degrees to the surface. I'm then going to hold the block down. I'm going to draw around the block so I've got its full shape marked out on the paper. As you can see. And the advantage of this is now I can see what happens when I change the angle of the ray going into the block. Now if you remember from reflection, the angle between the ray and the normal is called the incident ray. So what I'm going to do is, instead of moving the laser, I'm going to move the block. I'm going to turn it at an angle. Make sure that the laser is lining up with the point at which the normal strikes the surface. Now, we can see a change in direction. That change in direction, that bending of light, is caused by the change in speed of light when moving into the material. If the light enters the block at 90 degrees to the surface or along the normal, the light changes speed, it does refract, but there is no noticeable bend in the light, no noticeable change in direction. However, at an angle, which we'll mark in, I, the angle of incidence, we will notice a change. Now we want to be able to draw this ray diagram, so what I'm going to do, I've already got this point marked, the point where the light is hitting the intersection between the normal and the block. I'm going to mark a wee dot onto this ray and do the same with the ray on the other side, showing where the light enters. Now if I remove the block, I'll be able to connect the lines. So if the rays entering the block and exiting the block and in between. What we normally do here is draw arrows on our diagrams to show the direction of the light as it's traveling through the block. Now, one interesting curious fact, if I turn this ray diagram around and put the block back, we see that the ray follows the exact same path, and that's called reversibility of the path of light. Now, on this point here, where the light exited the block, I'm going to draw another normal at 90 degrees. And I can now mark a second angle. And that's R. So previously, when we were looking at reflection, I was the angle of incidence and R was the angle of reflection. Now, R is the angle of refraction. I can continue these normal lines into the block. And mark in the next two. So this is my angle of refraction inside of the block, and this is my angle of incidence inside of the block. Now what do we notice here? Well, we notice that going into the block, if I just line that back up again, going into the block, the ray bends towards the normal. So this angle of incidence here is much larger than that angle of refraction. When we look at the other side, the angle of refraction here is much larger than the angle of incidence. And we see this typically in all media. When we move from a less dense medium to a more dense medium, less dense air, more dense perspex, we refract towards the normal. When we go from a more dense medium, the more dense perspex, to the less dense medium, the air, we refract away from the normal. So we can use this to predict the path of the light going in, going out. To show this, I'm going to turn off the laser. Okay, another blank bit of paper. Draw around my block again. Roughly. I'm going to draw another normal line and 90 degrees to the surface. And just randomly an incident line. This time I'm going to make it much shallower. So here's my incident ray going into the block. Here's my angle of incidence. I'm now going to draw the angle of refraction. I know that I'm going from a less dense medium air into a more dense medium perspex. So that means my angle of refraction is going to be less. As we move from a less dense to a more dense, the angle of refraction means that we're going to go towards the normal. So this would be the same. I can move my ruler and draw what I would predict to be the path of light going through the perspex block. This might not be exactly what it's going to be. We can check it in a minute. However, the shape will be the same. Now, how do we draw the line coming out? Well, with the diagram previously, which we did with the laser, if we look closely, we can actually see that this line here, the incident ray, and this line here, the refracted ray, they're actually parallel with each other. So I'm going to use this fact with my predicted diagram. That. Draw my arrows as I normally would. Draw my second normal. And we see the same pattern. The angle of refraction inside of the perspex block is less than the angle of incidence outside. Here, the angle of incidence inside the perspex block is smaller than the angle of refraction outside. Let's just check this with a laser. Might not be exact, but it'd be interesting to see how close it is. That's actually pretty good. Not bad at all. Pretty much follows the exact path. Now this path will change. The amount that the light refracts will change depending on the material you're using. Glass and perspex have different densities, and so they have different refractive indices. The refractive index given by the symbol N, no unit, gives us an idea of how much refraction is going to take place. In higher physics, we actually look at measuring these angles with a protractor, and we see that N is equal to sine theta 1 over sine theta 2, where theta 1 is the angle in air, or the less dense medium, and theta 2 is the angle in perspex, or the more dense medium. Because the angle of incidence in air is always greater than the angle of refraction within the perspex block, N will always be a number 1 or more. 1 is the refractive index of a vacuum.